I've talked a lot about using polynomials to approximate functions. But what I want to do in this video is actually show you that the approximation is actually happening. So right over here, and I'm using Wolfram Alpha for this. It's a very cool website. You can do all sorts of crazy mathematical things on it. So it's wolframalpha.com, and I got this copied and pasted from them. I met Stephen Wolfram at a conference not too long ago. He said, yes, you definitely use Wolfram Alpha in your videos. And I said, great, I will. And so that's what I'm doing right here. And it's super useful because what it does is, and we could have calculated a lot of this on our own or even done it on a graphing calculator, but you literally can do it just with one step on Wolfram Alpha, is see how well we can approximate sine of x using a you could call it a Maclaurin series expansion, or you could call it a Taylor series expansion at x is equal to 0, using more and more terms, and having a good feel that for the fact that the more terms we add, the better it hugs the sine curve. So this over here in orange is sine of x. That should hopefully look fairly familiar to you. And in previous videos, we figured out what that Maclaurin expansion for sine of x is. And Wolfram Alpha does it for us as well. They actually calculate the factorials. 3 factorial is 6. 5 factorial is 120, so on and so forth. But what's interesting is here is you can pick how many of the approximations you want to graph. And so what they did is, if you want just one term of the approximation, so if we didn't have this whole thing, if we just said that our polynomial is equal to x, what does that look like? Well, that's going to be this graph right over here. They tell us which term, how many terms we used by how many dots there are right over here, which I think is pretty clever. So this right here, that is the function p of x is equal to x. And so it's a very rough approximation, although for sine of x, it doesn't do a bad job. It hugs the sine curve right over there, and then it starts to veer away from the sine curve again. You add another term. So if you have the x minus x to the third over 6, so now you have 2 terms in the expansion. So, or I guess we should say is that we're up to the third order term, because that's how they're numbering the dots. Because they're not talking about the number of terms, they're talking about the order of the terms. So they have 1 dot here because we have only one first degree term. When we have 2 terms here, since we kind of, when you do the expansion for sine of x, it doesn't have a second degree term. We now have a third degree polynomial approximation. And so let's look at the third degree. We should look for 3 dots. That's this curve right over here. So if you just have that first term, you just get that straight line. You add the negative x to the third over 6 to that x. You now get a curve that looks like this. Now gets a curve that looks like this. And notice, it starts hugging sine a little bit earlier, and it keeps hugging it a little bit later. So once again, just adding that second term does a pretty good job. It hugs the sine curve pretty well, especially around smaller numbers. You add another term, and now we're at an order 5 polynomial right over here. So x minus x to the third over 6 plus x to the 5th over 120. So let's look for the 5 dots. So that's this one right over here. 1, 2, 3, 4, 5. So that's this curve right over here. And notice it begins hugging the line a little bit earlier than the magenta version, and it keeps hugging it a little bit longer. So then it keeps hugging it a little bit. It keeps hugging it a little bit longer. Then it flips back up like this. So it hugged it a little bit longer. And you can see, I'll keep going. If you have all these first 4 terms, gives us a 7th degree polynomial. So let's look for the 7 dots over here. So they come in just like this. They come in like this. And then once again, it hugs the curve sooner than when we just had the first 3 terms. And it keeps hugging the curve all the way until here. And then the last one, if you have all of these terms up to x to the 9th, it does it even more. You start here, hugs the curve longer than the others, and goes out. And if you think about it, it makes sense, because what's happening here is each successive term that we're adding to the expansion, they have a higher degree of x over a much larger number. So for small x values, so when you're close to the origin, for small x values, this denominator is going to overpower the numerator, especially when you're below 1, because when you take something that has absolute value less than 1 to a power, you're actually shrinking it down. So when you're close to the origin, these latter terms don't matter much. So you're kind of not losing some of the precision of some of the earlier terms. When these tweaking terms come in, these come in when the numerator can start to overpower the denominator. So this last term, it starts to become relevant out here. It starts to become relevant out here, where all of a sudden x to the ninth can overpower 362,880, and the same thing on the negative side. So hopefully this gives you a sense. We only have 1, 2, 3, 4, 5 terms here. Imagine what would happen if we had an infinite number of terms. I think you'd get a pretty good sense that it would kind of hug the sine curve out to infinity. So hopefully that makes you feel a little bit better about this. And for fun, you might want to go you can type in Taylor expansion at 0 and sine of x, or Maclaurin expansion or Maclaurin series for sine of x, cosine of x, e to the x at wolframalpha.com, and try it out for a bunch of different functions, and you can keep adding or taking away terms to see how well it hugs the curve.